In this example now, we have a wire with a current 1.25 amps flowing into the page or away from us. It's 10 centimeters above the origin. We'd like to find the magnetic field 15 centimeters to the origin. So this is an example showing how to find the magnetic field if things aren't always up and down or right and left. Our current carrying wire, so this is a wire oriented this way, the current flows away from us. We know that the magnetic field is big circles around the wire. We can draw those circles. The orientation, our thumb goes into the page. We see what our fingers do. They come around this way. So the magnetic field comes around this way. We know that the magnetic field at point P is a tangent to the circle. So we ask, what does a tangent mean? We can think of it as perpendicular to the radius if we'd like to do that. Or we can think about our tangent. So our magnetic field can either go up and right or down and left. What are our circles doing? So our thumb goes into the page, our knuckles go at point P, our fingers point down and left. The magnetic field is down and left. Okay, so it's a tangent to the circle with the orientation given by the right-hand rule. So there's our magnetic field B. Let's see. We could find out the angle just now, but let's find the magnitude first, and then we'll sort out the direction afterwards. So for the magnitude of our magnetic field B, that's mu naught times I divided by 2 times pi times r. R we drew in our picture. Mu naught is 4 pi times 10 to the minus 7 Tesla meter over amps. Multiply by our current, 1.25 amps. Divide it by 2 times pi times r. Now, we don't know r, but we see that it's the hypotenuse of a right-angled triangle, so we can figure out r. r is the square root of 0.10 meters squared plus 0.15 meters squared. The distance from here to here, then, r is equal to 0.180 meters. Put that in our equation. We get that the magnitude of our magnetic field now is 1.39 times 10 to the minus 6 teslas. What about our direction? Because magnetic field is a vector. Well, this is a right angle. That makes this a right angle triangle. If we use our trig, this is an angle we can find. I'm going to label that theta. If I want to find theta, I know that tan theta is 10 over 15 centimeters. So theta is the inverse tan of 10 centimeters over 15 centimeters equals 33.7 degrees. Okay, that one's not difficult. What next? Okay, so we said the radius of the circle was like this. We said that the magnetic field was tangent to this. So these two things are perpendicular. R and B are perpendicular. That means this angle theta plus this angle beta, they have to be 90 degrees because these two things are perpendicular. Radius and B are perpendicular because B is tangent to the circle. So this angle beta then is 90, subtract 33.7 degrees equals 56.3 degrees. From here we have two choices for writing our magnetic field as a vector. It's probably easiest to write it in polar notation. Our magnetic field B is 1.39 times 10 to the minus 6 teslas at 56.3 degrees below the negative x-axis. If you prefer to give it in unit vector notation, then we can find the components of our vector. There is by. There is bx. We see that bx points left, so it's negative. It's adjacent to the angle beta, so we'll use cosine to figure it out. by points down, so it's negative. It's opposite the angle beta, so we use sine to figure that out. In unit vector notation, then, b would be negative 0.755i minus 1.16j. That would be times 10 to the minus 6 teslas. Either representation of the answer is fine, unless you were asked for a specific representation. Okay, let's try and fold in what we did before. Here's a current carrying wire. It makes a magnetic field. The example we did at the top of this lecture was what is the magnetic force on a current carrying wire in a magnetic field. Let's see if we can bring that in. So let's keep this example in the top of our minds and let's look at the next part. So for the next part, a 5-meter long wire with current 2.5 amps flowing out of the page is placed at our point P from our previous example. Let's find the magnetic force on it. So here's point P. We have a current carrying wire flowing out of the page. We can call that current I. What else? So we want to find the magnetic force on this wire. We know that the magnetic force FB is I times L cross B. Let's make sure we really understand what all these symbols are talking about. So this is the magnetic force on the wire that we placed at point P. On wire at P. This is the magnetic force on the wire carrying current I. So this is the current of the wire at point P. So I of the wire at point P. L means the length of the wire at point P. Okay, so this is the force on the wire. It's due to the current in the wire. The length of the wire is relevant. And the external field that this wire is sitting in, that's our field B. This external field B, external field, so this is the field outside. This one is made by this wire. Amp wire. So what's happening is there's a current in this wire. It makes a magnetic field that extends through space. This wire is sitting in that magnetic field, so it feels a force. If you started to ask questions like, well, doesn't this wire make a field? The answer to that question would be yes, it does make a field. Then if you asked, well, doesn't this wire feel a force? The answer to that question would also be yes. But this example specifically asks about the force on this wire. It doesn't ask about the force on this wire. That's why we're talking about this wire. It's because that's the topic of this example. So this wire makes a field. This wire sits in that field, so it feels a force. And that force is the thing we're going to figure out. From our previous slide, we did find the magnetic field at this point right here. Okay, so now let's see what we're going to sort out. We can either do the cross product or we can use the right-hand rule to do magnitude and direction. Why don't we do things that way? So the magnitude of our magnetic force is the current times the length times B times the sine of the angle between L and B. Okay, so our magnetic field is this direction. Our wire is in this direction. Our current is in this direction. Those two things are perpendicular. So the wire is perpendicular to the magnetic field. That's 90 degrees. So our magnetic force is the current in this wire, that's 2.50 amps, times the length of this wire, that's 5 meters, times the magnitude of the field that it's sitting in, 1.39, times 10 to the minus 6 teslas, times sine of 90, that's just 1. So the magnitude of our magnetic force is 1.7 times 10 to the minus 5 newtons. Okay, what about the direction? So since we did magnitude, we need to use our right-hand rule for the direction. When we do our right-hand rule, we extend our thumb in the direction of the length. Length and current have the same direction. Our index finger goes in the direction of B, so our index finger has to point like this. Then our extended middle finger shows the force, and our force is going to be perpendicular to B. So I is out of the page, B is down this way, force is coming down this way. So let's draw that force on the page. Just grab a different color pen for that. So my force, it's got to be perpendicular to both L and B, so that's perpendicular to both. I'll label that FB. And now, what about the direction of FB? Since we're going to go magnitude and direction, let's think about the angles that we know. This was an angle that we found. That was 33.7. This was an angle that we found. This was the one that we labeled beta. That was 56.3 degrees. we said that the magnetic force and the magnetic field are perpendicular. So these two are perpendicular. So now let's just look right here. So this is a straight line. All of the angles along a straight line, oh, better yet, we can do it this way. All of the angles along a straight line have to add to 180. So this plus this plus this equals 180. If you do it that way, we'll find this angle. We could also look at the fact that this makes an x, so this angle and this angle have to be the same. Yeah, two good ways to do it. 33.7 degrees. Okay, so the opposite angles in nx have to be the same, or these three have to add up to be 180. Whatever geometry you like better is the one you can use for figuring this out. So to write our FB as a vector, we would say FB equals 1.7 times 10 to the minus 5 newtons at 33.7 degrees below the positive x-axis, or below x. Okay, so it's a little bit more work when it's not straight up or down, but it's not too tough. You just have to be really careful with your geometry there.